Here we'll introduce similarity, but first let's make sure you remember congruence. Which two of these shapes are congruent to each other? If you're not sure, click down here to review. Right, these two triangles on the left are congruent. As you already know, shapes are congruent if you can turn one into the other by moving, rotating, or flipping it. So you can show that these two triangles are congruent if you move one of them on top of the other, and then flip it, showing they are indeed the same triangle. Let's take another look at these four shapes over here. None of them is congruent to this blue one, but which of these other shapes is a smaller version of the blue shape? Exactly right, it's this gray shape. If we were to make the blue shape a little smaller, and then move it over, you can see that they're now the same. So now we're ready to define similarity. Shapes are said to be similar if you can turn one of them into the other by moving it, rotating it, flipping it, or scaling it, which means making it bigger or smaller, kind of like zooming in or out. By the way, another word you might hear instead of scaling is dilating, which means the same thing, making something bigger or smaller. Okay, so take a look at these 6 shapes here. Which 3 of these would you say are similar to each other according to this definition? In other words, which of these have the same overall shape but perhaps a different size? Excellent work! These 3 are similar. We can turn the yellow shape into the green one by moving it and scaling it down, which means making it smaller. We can also turn this gray shape into the green one by moving it, rotating it, and scaling it down. Try another example. So among these 6 shapes here, which 3 are similar to each other? Right, these 3 shapes, which are all circles, are similar to each other. It turns out that all circles are similar to each other. If you draw any 2 circles, you can always turn one of them into the other by moving, rotating, flipping, or scaling it. Actually, you don't even need to worry about rotating or flipping because circles are very symmetrical. Okay, last question. Which of these shapes are similar? That is, which of these shapes can you turn into each other using any combination of moving, rotating, flipping, or scaling? Before we get started here, let's make sure you remember what similarity means. Of these 4 shapes here, which 2 are similar? If you're not sure, click down here to review. Right, these 2 triangles are similar. When 2 shapes are similar, you can use that fact to help you find missing side lengths of the shapes. For example, suppose you know this side of the green triangle has length 5, and this side has length 6. And let's say you also know that this side of the yellow triangle has length 10. With this information, try finding the length of this side of the yellow triangle. If you're not sure, click over here and we'll figure this out together. Right, this side has length 12. Each side of this larger triangle has twice the length of its corresponding or matching side of the smaller triangle. So this side of length 10 is twice as long as this corresponding side of length 5, and this side of length 12 is twice as long as this corresponding side of length 6. Let's come up with a general strategy for finding side lengths of similar shapes. Here are 2 similar shapes, and let's say this side has length 6, this side has length 9, this side has length 2, and this side over here has length x. And our goal is to use the fact that these shapes are similar and solve for x. The first step in solving these kinds of problems is to figure out which sides of the 2 shapes are corresponding. So which of these arrows here show pairs of corresponding sides? Exactly. This side of length 6 corresponds to this side of length 2, and this side of length 9 corresponds to this side of length x. The next step is to set up ratios. First, let's take the length of this side, 6, and divide it by the length of this side, 2. So this is a fraction, or ratio, that tells you how many times longer this side is than this side. So if you divide 6 by 2, you'll see that this side is 3 times longer than this side. Now because these shapes are similar, this ratio of 6 over 2 should be equal to the length of this side, 9, divided by the length of this side, x. So just to reiterate, this equation is saying that this side is a certain number of times longer than this side, and that should equal the number of times longer this side is than this side. And now we have an equation that you can solve for x. So what is x? Feel free to ask for a hint or two if you need help solving this equation. Great, so this side here has length 3. Let's look at one last example that you might see in the real world. Suppose there's a tall tree in your backyard whose height you want to measure. It would be a little too dangerous to climb this tree with a tape measure, but there are other ways to find its height. You find a nearby bush that's a lot shorter, and if you look carefully at these two plants, you'll notice that, along with their shadows, they form similar triangles. So let's use these triangles to find the height of the tree. You measure the height of the bush to be 4 feet, and the length of its shadow is 6 feet. Meanwhile, you run a tape measure along the ground and find the tree's shadow is 27 feet long. So using these similar triangles, how tall is this tree? Let's start this lesson off by making sure you remember what congruence is. Of the 4 triangles here, which 2 are congruent to each other? If you'd like to review congruence instead, click down here. Exactly right. This purple triangle and this blue triangle are congruent to each other. Suppose I tell you the side lengths of the purple triangle. This side has length 4, this side has length 2, and this side has length 5. Then what are the side lengths of this congruent blue triangle? Nicely done. So the corresponding sides in the 2 congruent triangles have the same length. And the same goes for the angles. These angles happen to be 23 degrees, 108 degrees, and 49 degrees. Because this triangle is congruent, that means these angles must also be 23 degrees, 49 degrees, and 108 degrees. Okay, so now for the big question. How many matching sides or angles must you know in order to say that 2 triangles are definitely congruent? For example, suppose you have 2 triangles. They may look congruent, but you can't be 100% sure. Maybe this side here is ever so slightly shorter than this side over here. But let's say you want to find out if they're really congruent. So you measure all the sides of this triangle, and let's say they have length lowercase a, b, and c. And then you measure the angles, and let's call their measures uppercase A, B, and C. When you measure the sides and angles of the second triangle, they match all the sides and angles of the first triangle. Okay, so these 2 triangles are definitely congruent. But what if you don't bother measuring the angles, and just found that the side lengths of the first triangle match the side lengths of the second triangle? Would that be enough to say that they're definitely congruent? What if you only measured 2 side lengths, or even just 1 side length? So let's start with 1 side length. If 2 triangles have 1 matching side length, is that enough to say that they're definitely congruent? Right. Having 1 matching side length does not guarantee that 2 triangles are congruent. For example, take a look at these 4 triangles down here, all of which have a side with length 5. The yellow and green triangles might be congruent, but the other ones are definitely not. So if triangles have 1 matching side, they're not necessarily congruent. Next, we'll look at triangles with 2 matching sides. So here's a triangle, and 2 of its side lengths are known. This red side has length 5, and this blue side has length 6. Now over here, you can use this interactive to make all kinds of triangles by dragging these 3 yellow corners around. Try making your own triangle with a side of length 5 and another side of length 6. Once you have one, press the Submit button up here. Great! So here's another example of a triangle with sides of length 5 and 6. Now these 2 triangles have 2 matching side lengths, but do they look congruent to you? So if triangles have 2 matching side lengths, is that enough to say that they're definitely congruent? Right, having 2 matching sides, like these triangles here, does not guarantee that triangles are congruent. So next, let's look at triangles with 3 matching sides. So here's another triangle, and all 3 of its side lengths are known. This red side has length 5, This green side has length 7, and this blue side has length 8. Try making your own triangle with sides of length 5, 7, and 8 over here. Once you've got one, press the Submit button up here. Great! So here's another example of a triangle with side lengths 5, 7, and 8. This triangle looks the same as the one on the left. It's just rotated a little bit, but they appear to be congruent. So if triangles have 3 matching side lengths, do you think that's enough to say that they're definitely congruent? So you think that if triangles have 3 matching side lengths, then they seem to be congruent. Let's figure out if this is really true or not using this sample triangle, or more specifically, the 3 side lengths of this triangle. How many different triangles can we make using these 3 sides? Well, let's build a triangle one side at a time, starting with this blue side. Next, let's attach the green side to one of the vertices, or corners, say this vertex on the left. Now by changing the angle between these 2 sides, we could make lots of different triangles. But remember, the third side of the triangle we're making has to be this long. So we need the distance between this vertex over here and this vertex over here to have the same length as this line segment. So which 2 orientations of the green side are possible so that this line segment can be the third side of our triangle? Right, these are the only 2 possible orientations for the green side. The green side could be up here, allowing us to add the third side of the triangle, or alternatively, it could be down here, again allowing us to add the third side of the triangle. So these are the possible triangles we can make whose 3 side lengths match those of the triangle up here. Sure enough, this top triangle is congruent to the original one, and you can see that this bottom triangle is also congruent if we move it on top of the original triangle and then flip it over. So yes, if triangles have 3 matching side lengths, then that's enough to guarantee that they're congruent. This fact is known as the side-side-side postulate, and you'll often see it abbreviated as SSS. Now as a final challenge, here are the side lengths for 6 different triangles, but you don't know any of the angles in these triangles. Which of these are congruent to each other? And here's a hint, there's more than 2.